The moon is more than just a glowing orb in our night sky. It's a powerful force that has shaped Earth's tides, climate, and even the length of our days for billions of years. Did you know that the moon is slowly drifting away from Earth at about 3.8 centimeters per year? Now imagine what would happen if, instead of drifting away, it suddenly collided with our planet. Do you know the devastating effects such a cosmic crash could unleash? The moon's current orbit and stability. What if the moon suddenly stopped orbiting Earth and started drifting closer? The consequences would be immediate and terrifying. The moon's gravity is already responsible for the tides we see each day, but if it moved closer, those tides would become monstrous, flooding coastlines and swallowing entire cities. This gravitational tug-of-war would also trigger massive earthquakes and volcanic eruptions as the Earth's crust strains under the added stress. The atmosphere wouldn't escape unscathed either. Violent storms and unusual weather patterns would sweep across the globe, making survival even harder. The moon's approach would disrupt the delicate balance that has kept Earth stable for billions of years, and the closer it got, the more chaotic life would become. This isn't just about water rising or storms intensifying. This is a complete upheaval of the planet's natural rhythms. The moon's pull would literally shake the ground beneath our feet, crack open the Earth's surface, and unleash forces that could reshape continents. It's a reminder that even our closest celestial neighbor plays a critical role in maintaining the balance of life on Earth. Without that balance, the planet would be a very different, far more hostile place. The initial approach and gravitational effects. The moon drifting closer to Earth wouldn't just cause wild tides and earthquakes. It would unleash a storm of atmospheric chaos like we've never seen. As the moon's gravity pulls harder, the air itself would become unstable, whipping up fierce winds and triggering massive storms that could rage non-stop. These wouldn't be ordinary storms. Think of hurricanes on steroids swirling across continents with relentless power. The interaction between charged particles from both Earth and the moon could even spark intense electrical storms, lighting up the sky with bolts far stronger than any lightning we know. This atmospheric turmoil would disrupt global weather patterns, making it nearly impossible to predict what comes next. Crops would fail, ecosystems would be thrown off balance, and the very air we breathe could become hazardous. The moon's approach would turn our skies into a battleground of natural forces, leaving no corner of the planet untouched. It's a stark reminder that the moon isn't just a silent companion lighting up our nights, it's a powerful force shaping life on Earth in ways we often overlook. As the chaos builds, survival would become a daily challenge, and humanity would have to adapt quickly or face the consequences of a planet thrown out of balance. Atmospheric and environmental chaos. The moment the moon crashes into Earth, the sheer force unleashed would be beyond anything humanity has ever witnessed. This isn't just a big explosion, it's a cataclysmic event releasing energy equivalent to billions of nuclear bombs detonating at once. The impact would instantly vaporize everything near the collision site, turning solid ground into molten rock and sending shockwaves racing around the globe. Debris from the collision would be hurled into the atmosphere and beyond, creating a fiery rain of molten fragments that would ignite wildfires worldwide. The sky would fill with thick clouds of dust and ash, blocking out sunlight and plunging the planet into darkness. This sudden blackout, known as an impact winter, could last for months or even years, causing temperatures to drop drastically and disrupting the delicate balance of life. Plants would struggle to survive without sunlight, and the collapse of ecosystems would ripple through the food chain, threatening countless species with extinction. The moon's collision wouldn't just reshape the surface of Earth, it would rewrite the story of life itself, forcing every living thing to face an uncertain and hostile world. This event would mark one of the most dramatic turning points in Earth's history, a reminder of how fragile our planet's stability truly is. Collision impact energy. So what would actually happen after the moon's catastrophic impact with Earth? Well, the immediate aftermath would be a global firestorm of unimaginable scale. The tremendous energy from the collision would superheat the atmosphere, igniting every combustible surface across continents. Forests, cities, everything would be engulfed in an inferno. As these firestorms raged, they'd pump colossal amounts of soot, ash, and greenhouse gases into the atmosphere, creating a thick, dark shroud that would completely block out the sun for months or maybe even years. This extended period of darkness, known as an impact winter, would cause global temperatures to plummet drastically. Photosynthesis, which is the fundamental process supporting most life on Earth, would just grind to a halt. The chilling temperatures, combined with the lack of sunlight, would decimate plant life, leading to a catastrophic collapse of food chains. The air itself would become unbreathable, filled with toxic gases and fine particles from the fires and pulverized debris. Surviving any initial impact would only be the beginning of a desperate struggle against a dying world, one that's been transformed into a barren, frozen landscape where the conditions for life as we know it would basically cease to exist. Global firestorms and darkness. When the moon collides with Earth, it won't just shake the planet, it'll fundamentally alter how our world spins. The impact's immense force would change Earth's rotation speed, possibly making days longer or shorter in ways we just can't predict. Imagine waking up to a day that lasts 30 hours or maybe just a few minutes shorter than usual. Our entire sense of time would be thrown off. The collision could even tilt Earth's axis, which is what gives us our seasons. Even a slight change in this tilt could lead to extreme climate shifts, with some regions facing brutal, never-ending winters, while others deal with scorching, relentless summers. This disruption to Earth's natural rhythms would affect everything: weather patterns, animal migration, and plant growth cycles. Over time, these changes could make huge parts of the planet hostile to life as we know it. The delicate balance that's allowed civilizations to thrive for thousands of years would be shattered, forcing humanity to adapt to a drastically different environment. It's a stark reminder that the moon isn't just a pretty object in the night sky. It actually plays a vital role in keeping our planet stable and life-supporting. Without it, Earth's future would be uncertain and filled with challenges we can barely imagine. Changes to Earth's rotation and orbit. The aftermath of a Moon-Earth collision wouldn't just leave a scar on the surface. It would create a massive cloud of debris orbiting our planet. This debris, made up of pulverized rock and dust, could actually form a spectacular ring around Earth, kind of like Saturn's iconic bands. Over time, some of this material might clump together, gradually forming a new moon. But this new satellite wouldn't be the gentle, familiar moon we know. It could be irregularly shaped, unstable, and constantly shifting. This debris ring or new moon would dramatically affect Earth's tides, possibly causing unpredictable flooding and altering marine ecosystems. Nights could become brighter or darker, depending on the density of the debris, disrupting animal behaviors and human activities alike. The constant presence of this debris would also pose a hazard to satellites and spacecraft, making it a lot more complicated to explore space or use the satellite technology we rely on for communication and navigation. This cosmic aftermath would remind us that even after a catastrophic event, the universe keeps moving, reshaping itself in ways that are both beautiful and dangerous. Life on Earth would have to adapt, not just to the immediate destruction, but to a changed celestial environment that could influence our planet for thousands, if not millions of years. Formation of a new debris ring or moon. So, the collision between the moon and Earth would trigger an extinction-level event unlike anything in recorded history. The immediate shockwaves, massive fires, and impact winter would, devastate ecosystems, wiping out countless species in just a matter of weeks. But the ripple effects would extend far beyond the initial disaster. Food chains would collapse as plants die off from lack of sunlight, and animals would really struggle to find enough resources to survive. Human civilization, which is so dependent on stable climates and agriculture, would face unimaginable challenges. Societies might collapse under the strain of famine, disease, and social unrest. Yet, even in the face of such destruction, life has a remarkable ability to endure. Microbial life, hidden deep underground or in the oceans, could survive the harsh conditions and serve as the foundation for eventual recovery. Over thousands or even millions of years, new species might evolve to fill the ecological niches left vacant. This event would mark a brutal reset for life on Earth, but it wouldn't necessarily be the end. It's a powerful reminder of both the fragility and resilience of life, showing just how closely our fate is tied to the cosmic forces that shape our planet. Potential extinction-level event. The moon crashing into Earth would unleash geological chaos that reshapes the planet for millions of years. The impact's force would fracture the crust, triggering massive volcanic eruptions worldwide. These eruptions would spew ash and lava, further darkening the skies and poisoning the air. Mountains could rise or crumble, and new landforms would emerge as the Earth's surface is violently rearranged. This geological upheaval would not only change the landscape, but also disrupt the planet's internal heat flow, potentially altering tectonic activity for ages. Earthquakes would become more frequent and severe, making the ground unstable and dangerous. Over time, these changes would create a planet that looks and feels completely different from the one we know today. The scars of the collision would be etched into the very bedrock, a permanent reminder of the cosmic disaster. Yet this process of destruction and renewal is part of Earth's natural cycle, though on a scale far beyond anything experienced in human history. It's a powerful testament to the dynamic nature of our planet and how it responds to forces from beyond our world, forever changing the stage on which life plays out. Long-term geological changes. The aftermath of a Moon-Earth collision would raise a crucial question. Could life ever bounce back from such devastation? Despite the overwhelming destruction, Earth's resilience is remarkable. Deep beneath the surface, microbial life forms could survive the harsh conditions, tucked away from the worst of the fires, radiation, and freezing darkness. These tiny survivors would become the seeds of a new beginning, slowly repopulating the planet's ecosystems over millions of years. Evolution would take its course, with new species emerging to fill the void left by those wiped out. However, this recovery wouldn't be quick or easy. The planet's environment would be radically altered, with unstable climates and landscapes posing constant challenges. Human civilization, if it survived, would have to adapt to a world unrecognizable from the one we know today. This long road to recovery highlights the incredible tenacity of life and the delicate balance that sustains it. While the Moon's collision would mark an end to an era, it wouldn't necessarily spell the end of life itself. Instead, it would reset the clock, offering a harsh but fascinating glimpse into nature's ability to endure and evolve, even after the most catastrophic events. Could life ever recover? The Moon's collision with Earth would be a cosmic catastrophe, but it also reveals something profound: the fragile yet extraordinary balance that sustains life on our planet. This event would shatter the harmony that has allowed ecosystems to flourish and civilizations to rise. Yet it's a powerful reminder that Earth exists within a vast and dynamic universe, where celestial bodies constantly influence one another in ways both subtle and dramatic. The Moon's presence stabilizes Earth's tilt, moderates tides, and even affects the length of our days. Without it, or after such a catastrophic collision, the world would be unrecognizable, chaotic, unstable, and harsh. But this scenario also highlights humanity's place in the cosmos. Small, vulnerable, yet capable of incredible resilience and adaptation. While the Moon crashing into Earth is an almost impossible event, thinking about it helps us appreciate the delicate cosmic dance that makes life possible. It encourages us to protect our planet and understand our universe better, knowing that even the most familiar celestial neighbor plays a vital role in the story of life. So, next time you look up at the Moon, remember, it's not just a glowing rock in the sky, but a guardian of Earth's balance and a key player in the ongoing saga of our planet. Thanks for joining us on Space Facts today. If you enjoyed exploring what would happen if the Moon collided with Earth, make sure to hit that bell icon so you never miss out on our cosmic discoveries. Don't forget to subscribe for more mind-blowing space content delivered straight to your feed. We'd love to hear your thoughts. Drop a comment below and tell us which space fact amazed you the most, or what topic you want us to cover next. Stay curious, and keep looking up. The Sun is so massive that it contains 99.8% of all the mass in our solar system, dwarfing every planet, including Earth. Yet Earth's water, covering 71% of its surface, holds the key to life as we know it. Here's a striking thought. If we poured all of Earth's water onto the Sun, it would barely make a ripple. Did you know just how tiny our planet's water is compared to the vastness of the Sun? Let's uncover what really happens in this cosmic showdown. The sheer volume of Earth's water. Earth's water is staggering in scale. About 1.4 billion cubic kilometers of it spread across oceans, rivers, lakes, and underground reservoirs. This vast quantity covers around 71% of our planet's surface, shaping climates, ecosystems, and life itself. But when you compare this to the Sun, the numbers tell a different story. The Sun is a colossal ball of plasma with a volume roughly 1.4 million times greater than Earth's. So even if we could somehow gather every drop of water on Earth and pour it onto the Sun, it would be like adding a single teaspoon to an Olympic-sized swimming pool. This comparison highlights just how immense the sun truly is. While Earth's water seems endless to us, it's practically negligible on a cosmic scale. Understanding this contrast not only puts our planet's resources into perspective but also sparks curiosity about how such a relatively tiny amount of water would behave in the sun's extreme environment. This sets the stage for a fascinating exploration of what would really happen if Earth's water met the fiery surface of our nearest star. The sun's enormous scale. The sun isn't just big, it's unimaginably massive. When you hear that the sun's volume is about 1.4 million times that of Earth, it's hard to grasp what that really means. To put it simply, if Earth were the size of a small marble, the sun would be a gigantic beach ball towering over it. This vast difference in scale means that even the entirety of Earth's water, which feels endless to us, is just a tiny speck compared to the sun's sheer size. The sun's enormous volume is made up of scorching hot plasma, a state of matter so extreme it's unlike anything we experience on Earth. This immense size and energy output allow the sun to sustain nuclear fusion, the process that powers its light and heat. So when thinking about pouring all Earth's water onto the sun, it's like trying to fill a massive ocean with a single bucket of water. The sun's colossal scale means that this water would barely make a dent, swallowed instantly by the star's overwhelming mass and energy. This contrast between Earth and the sun's size sets the stage for understanding why such a dramatic idea, pouring all our planet's water onto the sun, would have surprisingly little impact on the star itself, even though it would be catastrophic for life here on Earth. What is the sun made of? The sun is not just a giant ball of fire, it's a swirling mass of plasma, mostly hydrogen and helium, existing in a state that's completely alien to us. About 74% of the sun's composition is hydrogen, with helium making up roughly 24%, and the rest are trace elements. This plasma state means the sun's gases are so hot and energized that electrons are stripped from atoms, creating a soup of charged particles. Unlike the water we're familiar with on Earth, which is liquid and cool, the sun's surface temperature is around 5,500 degrees Celsius, and its core reaches an astonishing 15 million degrees Celsius. In this environment, water molecules can't survive. They would instantly break apart into hydrogen and oxygen atoms. This extreme heat and energy make the sun a nuclear fusion reactor, where hydrogen atoms fuse to form helium, releasing immense energy that powers life on Earth. So when thinking about pouring Earth's water onto the sun, it's important to remember that the sun isn't a solid surface or a cool body of water. It's a blazing, electrified plasmasphere where water can't exist in any familiar form. This fundamental difference in composition and state of matter explains why Earth's water would be completely transformed the moment it touched the sun's atmosphere, setting the stage for what happens next in this cosmic experiment. What happens to water near the sun? Well, water and the sun are a recipe for instant transformation. The moment any water from Earth approached the sun, it wouldn't stay liquid for even a fraction of a second. The sun's surface temperature is about 5,500 degrees Celsius, hot enough to vaporize water instantly. But it doesn't just evaporate like steam from a boiling kettle. The intense heat breaks water molecules apart into their basic elements, hydrogen and oxygen atoms. These atoms then become ionized, meaning they lose electrons and turn into charged particles, blending seamlessly into the sun's already roiling plasma. This process happens so quickly and violently that the water essentially disappears, losing all its original form. Instead of a splash or steam cloud, the water's atoms become part of the sun's fiery atmosphere, carried away by solar winds or absorbed deeper into the star. This extreme environment ensures that Earth's water would never accumulate or create any visible effect on the sun's surface. So, pouring all of Earth's water onto the sun wouldn't cause a dramatic explosion or change. It would be a silent, instantaneous absorption into the star's blazing furnace, highlighting just how hostile and powerful the sun truly is. Would the water affect the sun's composition? Adding all of Earth's water to the sun might sound like it could change the star's makeup, but in reality, it's barely a drop in the cosmic ocean. The sun's mass is about 330,000 times that of Earth, and its composition is overwhelmingly hydrogen and helium. When water, made of hydrogen and oxygen, arrives, it's such a tiny addition compared to the sun's massive volume that it won't noticeably shift the star's elemental balance. The hydrogen from water would simply blend into the sun's existing hydrogen supply, while the oxygen atoms would be quickly ionized and absorbed into the plasma. This means the fusion reactions that power the sun would continue unaffected, as they rely on hydrogen nuclei colliding under immense pressure and temperature in the core. The sun's immense energy output and gravity dwarf any influence Earth's water could have. So despite the dramatic idea of pouring all our planet's water onto the sun, it wouldn't alter the star's composition or behavior in any meaningful way. This highlights the incredible scale and power of the sun compared to our home planet, emphasizing how small Earth's resources are in the grand scheme of the cosmos. Could the oxygen from water cause any reaction? Oxygen might seem like a wild card when it comes to pouring Earth's water onto the sun, but it wouldn't cause any dramatic fireworks. Once water molecules break apart near the sun, oxygen atoms become ionized, stripped of their electrons, and merge into the sun's plasma environment. This plasma is already a chaotic mix of charged particles, so the oxygen simply becomes part of that turbulent sea. Unlike on Earth, where oxygen supports combustion, the sun's extreme heat and pressure prevent any typical chemical reactions. The oxygen atoms don't ignite or explode. Instead, they're absorbed and dispersed by the sun's immense energy and magnetic fields. This means no sudden bursts or new solar phenomena would arise from the oxygen alone. The sun's fusion process, fueled by hydrogen nuclei, remains untouched by this tiny addition of oxygen. So, while oxygen is essential for life on Earth, in the sun's blazing furnace, it's just another particle swept up in the endless dance of plasma and energy. This shows how different the sun's environment is from anything we experience, turning familiar elements into something entirely alien. What about the sun's energy output? So, what about the sun's energy output? Well, the sun's power actually comes from deep within its core, where nuclear fusion transforms hydrogen into helium, releasing immense energy that lights up our entire solar system. This energy output is so vast that honestly, adding Earth's entire supply of water on the sun's surface wouldn't cause any noticeable change at all. The fusion process really depends on conditions in the core, temperatures of around 15 million degrees Celsius and crushing pressure, not on what happens at the surface or in the outer layers. Water, once it's vaporized and broken down, just becomes part of the sun's plasma without affecting the core's reactions. The sun's brightness, heat, and energy output remain steady because they're governed by these internal fusion processes, which are, honestly, far beyond the influence of any external material like Earth's water. So, this means that no matter how much water we pour onto the sun, it won't brighten, dim, or flare up in response. Understanding this really helps us appreciate the incredible stability and power of our star, which just keeps shining brightly, totally unaffected by even the most dramatic additions from our tiny planet. Would this water cause solar phenomena? Solar activity like flares and sunspots might seem like they could be influenced by adding something new to the sun's surface, but Earth's water wouldn't trigger any of these phenomena. These solar events are driven by the sun's complex magnetic fields and plasma dynamics deep within its atmosphere, not by external substances. When water reaches the sun, it's instantly vaporized and broken down into atoms that blend into the plasma without disturbing the magnetic forces at play. The sun's magnetic field lines twist and snap due to internal motions and charged particle flows, causing solar flares and sunspots, processes far removed from any material we might add on the surface. So, pouring all of Earth's water onto the sun wouldn't spark new solar storms or alter existing ones. Instead, the water's atoms would simply become part of the sun's vast, turbulent environment, invisible and insignificant against the backdrop of these powerful magnetic phenomena. This highlights just how dynamic and self-contained the sun's activity is, governed by forces and energies far beyond anything Earth can contribute. Could this water create a visible effect? Any hope of seeing a dramatic splash or cloud when pouring Earth's water onto the sun quickly fades under the star's intense conditions. The water wouldn't linger or create visible effects like steam or mist. Instead, it would be instantly vaporized and broken down into individual atoms, which would then be swept into the sun's seething plasma atmosphere. This process happens so rapidly and thoroughly that no splash, plume, or cloud would form to catch the eye. The sun's surface is a roiling sea of charged particles and magnetic fields, where anything foreign is quickly absorbed and dispersed. So, rather than a spectacular visual, the water's atoms quietly vanish into the sun's fiery environment, becoming part of the endless energetic dance that powers our star. This invisibility of Earth's water on the sun's surface underscores just how extreme and overwhelming the sun's environment is, turning something as familiar as water into an unnoticeable drop in a blazing ocean. Earth's water is precious. Earth's water might seem endless to us, but it's a finite treasure that sustains every form of life on our planet. Losing it all to the sun would mean the complete collapse of ecosystems, agriculture, and human civilization. While it's fascinating to imagine pouring all that water into the sun and watching it vanish, the reality is that Earth's water is irreplaceable and vital. This cosmic thought experiment highlights just how precious and unique our planet's resources are in the vastness of space. The sun, with its immense power and size, remains unaffected by such a small addition. But for Earth, water is the foundation of life, climate, and even our future. Protecting and valuing this resource is crucial because, unlike the sun's endless energy, Earth's water is limited and fragile. So while the idea of sending all our water into the sun sparks curiosity and wonder, it ultimately reminds us to cherish and safeguard the life-giving liquid that makes our world so extraordinary. What other cosmic questions or wild ideas do you want to explore next? Let me know. Thanks for exploring this cosmic journey with Space Facts. If you enjoyed uncovering what would happen if all of Earth's water poured onto the sun, don't forget to hit that subscribe button and ring the bell icon so you never miss an out-of-this-world fact. We love hearing your thoughts, so drop a comment below. What other space mysteries should we dive into next? Keep looking up and stay fascinated. So, Earth's orbit around the sun isn't a perfect circle, it's actually an ellipse, which means our planet gets closer to the sun at some times and farther away at others. At perihelion, Earth is about 5 million kilometers closer to the sun than at aphelion, but surprisingly this doesn't cause the hottest or coldest seasons. Here's the striking punchline. Earth's seasons are driven more by its tilt than its distance from the sun. Did you know this fascinating fact before? What is perihelion? Well, Earth's orbit around the sun is far from a perfect circle. It's an ellipse, which means the distance between Earth and the sun changes throughout the year. One of the most fascinating points in this journey is called perihelion, the moment when Earth is closest to the sun. This event usually happens around January 3rd when the distance shrinks to about 147 million kilometers. At perihelion, Earth is roughly 5 million kilometers closer to the sun than at other times, which might make you think it's hotter then. But here's the twist. Perihelion actually occurs during the northern hemisphere's winter. This surprising fact reveals that Earth's seasons aren't driven by how close we are to the sun, but rather by the tilt of our planet's axis. Another interesting aspect of perihelion is that Earth speeds up in its orbit due to the sun's stronger gravitational pull, moving faster than at any other point in the year. This change in speed follows Kepler's laws of planetary motion, showing how gravity shapes our planet's path. While the extrasolar energy Earth receives at perihelion, about 7% more than at aphelion, does have some subtle effects on climate, it's not enough to override the seasonal changes caused by axial tilt. Understanding perihelion gives us a clearer picture of Earth's dynamic relationship with the sun and helps scientists predict climate patterns and refine space navigation. It's a perfect example of how the cosmos operates with complexity and precision, influencing life on our planet in ways we're still uncovering. What is aphelion? Earth's orbit reaches its farthest point from the sun at a moment called aphelion, occurring around July 4th each year. At this time, Earth drifts out to approximately 152 million kilometers away from the sun, about 5 million kilometers farther than at perihelion. You might expect this distance to make summer cooler in the northern hemisphere, but surprisingly, it's the opposite. Aphelion coincides with the northern hemisphere's summer, reinforcing that the seasons are controlled more by Earth's axial tilt than by its distance from the sun. Even though Earth receives about 7% less solar energy at aphelion compared to perihelion, this difference is subtle and overshadowed by the tilt's effect on sunlight angle and day length. Another intriguing fact is that Earth slows down in its orbit at aphelion, moving more leisurely due to the weaker gravitational pull from the sun. This orbital speed change is a direct consequence of Kepler's laws, which describe how planets sweep out equal areas in equal times. The slower pace at aphelion slightly affects the length of seasons, making northern hemisphere summers a bit longer than winters. Aphelion also plays a role in shaping climate patterns, subtly influencing temperature variations and atmospheric dynamics. Understanding aphelion helps scientists model Earth's climate system more accurately and enhances our grasp of orbital mechanics. In essence, aphelion is a reminder of the elegant dance between Earth and the Sun, where distance, speed, and tilt combine to create the rhythms of life and weather we experience every year. Why does Earth's distance vary? Earth's orbit around the Sun isn't a perfect circle, and that elliptical shape is what causes the distance between Earth and the Sun to vary throughout the year. This variation is what creates the points known as perihelion and aphelion. But why does Earth's orbit take this shape in the first place? The answer lies in the gravitational forces exerted by the Sun and other planets, especially giant ones like Jupiter and Saturn. These forces tug and pull on Earth's path, stretching it into an ellipse rather than a circle. This elliptical orbit means Earth's distance from the Sun changes continuously, influencing not just the amount of solar energy we receive, but also the speed at which Earth travels around the Sun. Over thousands of years, these gravitational interactions cause subtle shifts in the orbit's shape and orientation, a phenomenon called orbital eccentricity. These changes can impact long-term climate patterns on Earth, contributing to cycles like the ice ages. Understanding the elliptical nature of Earth's orbit helps scientists explain why perihelion and aphelion happen when they do, and why the seasons don't line up simply with Earth's distance from the Sun. It's a complex cosmic dance shaped by gravity, momentum, and time, revealing how interconnected our solar system truly is. This knowledge not only deepens our appreciation for Earth's place in space but also improves climate models and space mission planning, showing that even the smallest orbital shifts can have far-reaching effects. Effect on Earth's seasons. Earth's seasons are often misunderstood as being caused by how close or far we are from the Sun, but the real driver is the tilt of Earth's axis. This tilt of about 23.5 degrees means that during different times of the year, either the northern or southern hemisphere leans toward the Sun, receiving more direct sunlight and longer days. Interestingly, Earth reaches perihelion, the closest point to the Sun, during the northern hemisphere's winter, while aphelion, the farthest point, occurs in its summer. This shows that the distance to the Sun plays a surprisingly minor role in seasonal temperature changes. Instead, the axial tilt controls how sunlight is distributed, creating the familiar cycle of spring, summer, fall, and winter. The tilt also affects the intensity of sunlight, making summers warmer and winters colder, regardless of Earth's varying distance from the Sun. However, the slight difference in solar energy received at perihelion and aphelion, about 7% more at perihelion, does have subtle effects on climate, such as influencing the length and severity of seasons in each hemisphere. For example, southern hemisphere summers tend to be a bit warmer and shorter because they coincide with perihelion. This complex interplay between Earth's tilt and its elliptical orbit shapes the unique climate patterns we experience year after year. Understanding this helps us appreciate why seasons don't simply follow Earth's distance from the Sun, but are a beautiful result of celestial mechanics working together. Impact on solar energy received. Ever wondered how much difference the Sun's distance really makes to the energy Earth receives? At perihelion, Earth is about 7% closer to the Sun than at aphelion, meaning it absorbs noticeably more solar energy. This increase might seem small, but it actually translates into a significant boost in the amount of sunlight hitting our planet's surface. This extra energy can influence weather patterns and temperature variations, especially in the southern hemisphere, which experiences summer during perihelion. The increased solar radiation can lead to warmer summers and slightly shorter winters there. Conversely, during aphelion, Earth receives less solar energy, which can contribute to cooler temperatures and longer winters in the northern hemisphere. However, this difference in solar energy is just one piece of the climate puzzle. The tilt of Earth's axis and atmospheric conditions play much larger roles in shaping our seasons and weather. Still, the variation in solar energy between perihelion and aphelion subtly affects global climate systems, influencing phenomena like monsoons, ocean currents, and even the timing of plant growth cycles. Scientists closely study these energy fluctuations to improve climate models and predict long-term changes. So, while Earth's distance from the Sun isn't the main reason for our seasons, it quietly fine-tunes the climate, reminding us that even small cosmic shifts can ripple through life on Earth in fascinating ways. Influence on climate patterns. The subtle dance between Earth's distance from the Sun and its climate patterns is more intricate than most realize. While the difference in solar energy between perihelion and aphelion is about 7%, this variation can subtly influence weather and climate systems across the globe. For instance, the southern hemisphere, which experiences summer during perihelion, tends to have slightly warmer and shorter summers compared to the northern hemisphere. This difference affects atmospheric circulation patterns, ocean currents, and even the timing of seasonal events like monsoons. The extra solar energy during perihelion can intensify weather phenomena, leading to shifts in rainfall and temperature distributions. Conversely, during aphelion, the reduced solar input in the northern hemisphere's summer can contribute to milder conditions. These subtle shifts, when combined with other climate drivers like ocean cycles and atmospheric composition, help create the complex and dynamic climate system we experience. Scientists study these effects closely, using data from satellites and climate models to understand how small changes in Earth's orbit influence long-term climate trends. This knowledge is crucial for predicting future climate scenarios and understanding natural climate variability. So while perihelion and aphelion don't dictate the seasons outright, their influence gently shapes the rhythms of Earth's climate, reminding us that even minor cosmic variations ripple through our planet's environment in fascinating ways. Earth's orbital speed differences. So, Earth's speed as it orbits the Sun isn't constant. It actually changes depending on how close or far it is from the Sun. When Earth reaches perihelion, the closest point to the Sun, it zips along faster due to the Sun's stronger gravitational pull. This increase in speed is a direct consequence of Kepler's laws of planetary motion, which explain that a planet moves quicker when it's nearer to the Sun and slower when it's farther away. Conversely, at aphelion, Earth moves more slowly because the Sun's gravitational grip weakens with distance. Now, this variation in orbital speed affects how long each season lasts. For example, the northern hemisphere's winter is shorter because it coincides with perihelion when Earth is moving faster. Meanwhile, summer in the northern hemisphere lasts longer as it occurs near aphelion when Earth's pace slows down. This subtle difference in orbital velocity influences the rhythm of our year and the timing of seasonal changes. Understanding these speed shifts helps scientists refine climate models and predict how Earth's orbit interacts with other celestial forces. It's a remarkable reminder that Earth's journey around the Sun is a dynamic, ever-changing dance governed by gravity and motion, shaping the very experience of time and seasonality on our planet. Historical changes in orbit. So, Earth's orbit isn't, fixed in stone. It actually changes slowly over thousands of years, mainly because of gravitational tugs from other planets, especially those massive ones like Jupiter and Saturn. These gravitational forces cause Earth's orbit to shift in both shape and orientation, and this whole process is called orbital eccentricity. Over really long timescales, this means the distance between Earth and the Sun at perihelion and aphelion isn't always the same, but instead, it varies in a pretty predictable cycle. These slow changes can have some pretty profound effects on Earth's climate, even contributing to natural cycles like the ice ages. When Earth's orbit becomes more elliptical, the difference between perihelion and aphelion grows, which actually amplifies those seasonal contrasts we feel. On the flip side, when the orbit is more circular, the seasonal differences tend to be a lot milder. This orbital variation, combined with other factors like axial tilt and precession, creates these really complex climate patterns over tens of thousands of years. Scientists study these cycles to help understand past climate changes and to predict future trends too. The shifting orbit also affects the timing of perihelion and aphelion, so these points actually move through the calendar gradually over millennia. This ongoing cosmic dance just highlights how dynamic our solar system is, and how interconnected planetary motions really influence life here on Earth. Understanding these long-term orbital changes honestly deepens our appreciation for the delicate balance that sustains our planet's environment, and it's a reminder that Earth's place in space is always evolving. Perihelion and aphelion in other planets. Not all planets orbit the Sun in perfect circles and, well, Earth is no exception. Just like our planet, other planets also have those points in their orbits called perihelion and aphelion, the closest and farthest distances from the Sun. But these distances can vary dramatically depending on each planet's unique orbit. For instance, Mercury, which is the closest planet to the Sun, has a highly elliptical orbit, so its perihelion and aphelion distances are really different, causing some extreme temperature swings. On the other hand, Venus has a nearly circular orbit, so its distance from the Sun barely changes throughout the year. Then, gas giants like Jupiter and Saturn have much larger orbits, so their perihelion and aphelion points are millions of kilometers apart, but the relative difference compared to their average distance is actually smaller. These variations affect each planet's climate, atmospheric conditions, and even the length of their years. By studying perihelion and aphelion across the solar system, scientists can better understand planetary climates, orbital dynamics, and how gravitational forces shape planetary paths. It also gives us insight into how Earth's orbit compares to others, really highlighting the delicate balance that sustains life here. This cosmic perspective is a good reminder that while Earth's orbit might seem unique, it's actually part of a vast interconnected system where every planet's journey around the Sun tells its own fascinating story. Why understanding these points matters. Understanding Earth's perihelion and aphelion isn't just about, distances and dates. It's actually a key to unlocking how our planet's climate and environment work. Scientists rely on really precise knowledge of these orbital points to improve climate models, which helps predict weather patterns and long-term climate changes. Satellites and space missions also benefit from this understanding, since accurate calculations of Earth's position relative to the Sun are crucial for navigation and communication systems. The subtle shifts in Earth's orbit influence everything from ocean currents to atmospheric circulation, shaping the conditions that sustain life. Plus, studying perihelion and aphelion deepens our understanding of celestial mechanics, showing just how gravitational forces govern planetary motion with incredible precision. This knowledge doesn't just stay on Earth, it also helps us explore other planets and their environments. By appreciating these cosmic rhythms, we gain insight into the delicate balance that keeps Earth habitable. It's a reminder that our planet's journey around the Sun is not just a simple orbit, but a complex dynamic dance with effects on our daily lives and our future. Engaging with these concepts connects us to the broader universe, inspiring curiosity and respect for the forces that shape our world. Thanks so much for joining us on this cosmic journey through Earth's perihelion and aphelion. If you enjoyed diving into these fascinating space facts, don't forget to hit that subscribe button and ring the bell icon so you never miss an update from Space Facts. We absolutely love hearing from you, so go ahead and drop a comment below with your thoughts or any questions you might have about our planet's orbit, or really anything space-related. Your curiosity is what keeps this channel alive and thriving. Until next time, keep looking up and stay curious. Mercury vanishes from our skies for months at a time, then suddenly reappears as a brilliant evening star that ancient civilizations called the messenger of the gods. This tiny world completes an entire orbit around the Sun in just 88 days, faster than any other planet in our solar system. But here's what blows my mind. Mercury can appear up to 28 degrees away from the Sun during maximum eastern separation, yet most people will never see it once in their entire lifetime. Did you know that Mercury is actually easier to spot than most stars when you know exactly when and where to look? What is eastern separation? You're looking up at the night sky, and there's Mercury. But wait, how is that even possible when everyone says it's impossible to see? That's where eastern separation comes into play, and it's absolutely fascinating. When we talk about eastern separation, we're describing the angular distance between Mercury and the Sun as seen from Earth. Think of it like this. The Sun is your reference point, and Mercury appears to separate or move away from it in the eastern direction of the sky. This separation is measured in degrees, just like how you'd measure angles in geometry class. The maximum eastern separation is when Mercury reaches its greatest angular distance from the Sun while positioned to the east of it. During this time, Mercury becomes visible in the evening sky right after sunset, appearing as a bright star-like object low on the western horizon. This phenomenon happens because Mercury's orbit is inside Earth's orbit, so from our perspective it appears to swing back and forth on either side of the Sun, like a pendulum. Eastern separation specifically means Mercury is trailing behind the Sun in its apparent motion across our sky. The beauty of maximum eastern separation is that it gives us the best opportunity to spot this elusive planet with our naked eyes. Without this separation, Mercury would be lost in the Sun's glare, making observation completely impossible for amateur stargazers. Why Mercury is special. You've probably tried spotting Mercury before and failed miserably, right? Don't worry, you're not alone. Mercury is hands down the most challenging planet to observe, and there's a perfectly good reason why astronomers have been frustrated with this little world for centuries. Mercury sits closest to the Sun in our solar system, which creates a unique problem that no other planet faces. While Mars, Jupiter, and Saturn can appear anywhere in our night sky throughout the year, Mercury is essentially chained to the Sun's vicinity. This proximity means Mercury never strays far from the solar glare that dominates our daytime sky. What makes Mercury truly special is its incredibly fast orbit. It completes one trip around the Sun in just 88 Earth days, which is why the Romans named it after their speedy messenger god. This rapid orbital motion creates a cosmic dance where Mercury alternately appears on the eastern and western sides of the Sun in quick succession. Unlike the outer planets that can be visible all night long, Mercury only gets brief windows of visibility during twilight hours. The planet's small size compounds the challenge. It's barely larger than our moon, making it appear as just a tiny dot even when conditions are perfect. This combination of proximity to the Sun, rapid orbital motion, and small size creates the perfect storm of observational difficulty that has made Mercury the holy grail for amateur astronomers worldwide. Maximum eastern separation defined. You know how Mercury usually hides in the Sun's glare? Well, maximum eastern separation is the exact moment when Mercury says, "Not today," and reaches its greatest possible distance from the Sun as seen from Earth. This isn't just some random astronomical event. It's a precisely calculated phenomenon that occurs when Mercury reaches approximately 18 to 28 degrees of angular separation from the Sun, depending on where Mercury is in its elliptical orbit. During this peak separation, Mercury appears furthest to the east of the Sun in our evening sky, which translates to the best possible viewing conditions you'll get for this elusive planet. The term maximum is crucial here because Mercury's separation from the Sun constantly changes as it orbits, swinging like a cosmic pendulum from maximum eastern separation to maximum western separation and back again. When astronomers say maximum eastern separation, they're pinpointing the exact day and time when this angular distance peaks before Mercury begins its journey back toward the Sun. This moment typically lasts only a few days, making it a fleeting opportunity that serious stargazers mark on their calendars months in advance. The beauty of this definition lies in its precision. It's not just when Mercury is visible, but rather the optimal moment when Mercury achieves its greatest possible visibility in the evening sky. Understanding this technical definition helps you appreciate why timing is everything when hunting for Mercury in the twilight hours. When this occurs. You're probably wondering when you can actually catch Mercury in action. And here's the fascinating part. Mercury's maximum eastern separations follow a predictable rhythm that repeats roughly every 116 days. This means you get approximately 3 opportunities per year to witness this celestial event, though the exact timing shifts slightly each year due to orbital mechanics. The separations don't happen randomly throughout the year. They cluster around specific months, typically occurring in late winter, late spring, and early fall for most observers in the northern hemisphere. What's really cool is that Mercury alternates between eastern and western separations, so if you miss an eastern separation in March, you might catch a western separation in May, then another eastern separation in August. The exact dates vary from year to year, but astronomers can predict these events decades in advance with incredible precision. Each maximum eastern separation event lasts about a week, with the peak occurring on one specific day when Mercury reaches its furthest angular distance from the Sun. However, Mercury remains reasonably visible for several days before and after this peak, giving you a practical viewing window of roughly 10 to 14 days. The timing also depends on your geographic location. Observers at different latitudes will experience slightly different optimal viewing periods. Southern Hemisphere observers get completely different seasonal patterns, with their best eastern separations occurring during opposite months compared to northern observers, making Mercury truly a global phenomenon with local variations. Best viewing conditions. You want to see Mercury? Then you need to become obsessed with timing, location, and atmospheric conditions, because Mercury doesn't forgive amateur mistakes. The absolute best time to hunt for Mercury during maximum eastern separation is during evening twilight, specifically 30 to 45 minutes after sunset, when the sky has darkened enough to reveal faint objects, but isn't completely black yet. This narrow window is non-negotiable because if you wait too long, Mercury will set below the horizon along with the fading twilight. Your viewing location matters enormously. You need an unobstructed western horizon, which means no buildings, trees, or mountains blocking your view in the direction where the sun just set. Urban light pollution can kill your chances, so, if possible, drive to a darker location away from city lights, where the contrast between Mercury and the sky background becomes more pronounced. Weather conditions can make or break your observation session. You need clear skies with minimal atmospheric turbulence, which means avoiding nights with high humidity, haze, or strong winds that cause excessive twinkling. The best atmospheric conditions occur during stable weather patterns, often a day or two after a cold front passes through your area. Seasonal timing also plays a role. Some maximum eastern separations occur when Mercury appears higher above the horizon than others, depending on the angle of the ecliptic relative to your local horizon. Spring separations are typically best for northern hemisphere observers, while fall separations favor southern hemisphere viewers. How to spot Mercury. You need to master the art of systematic sky scanning because Mercury won't announce itself with flashing lights. Start by finding where the sun set on the western horizon. That's your reference point for everything that follows. Mercury will appear somewhere along the ecliptic, which is the imaginary line that the sun, moon, and planets follow across our sky. During maximum eastern separation, look for Mercury roughly 15 to 25 degrees to the left of where the sun disappeared, depending on the specific separation angle. Here's the key trick most people miss. Mercury looks like a bright, steady star that doesn't twinkle as much as real stars do. It typically appears as a yellowish or orange-colored point of light, brighter than most stars but not as brilliant as Venus. The best strategy is to scan systematically from the sunset point leftward along the horizon, looking for any star-like object that seems out of place or brighter than expected. Mercury stays relatively low to the horizon, usually appearing no higher than the width of your fist held at arm's length above the western horizon. Don't expect Mercury to be obvious. It often appears dimmer than you'd anticipate, especially if atmospheric conditions aren't perfect. Use nearby bright stars or planets as reference points to help guide your search. If you spot what you think is Mercury, watch it for several minutes. Planets appear steadier than stars, which tend to twinkle more noticeably. The planet will also set relatively quickly, disappearing below the horizon within an hour or two of sunset. Equipment needed. So you can absolutely spot Mercury during maximum eastern separation with nothing more than your naked eyes. No telescope, no binoculars, no fancy gadgets required. This might, actually surprise you because Mercury has a reputation for being impossible to see, but during optimal separations, it appears bright enough to be visible without any optical aid whatsoever. However, binoculars can be your secret weapon for making the hunt much easier, especially 7x50 or 10x50 models that gather more light and provide a wider field of view. Binoculars really help you scan the twilight sky more efficiently and can reveal Mercury even when atmospheric conditions aren't perfect. They also make Mercury appear noticeably brighter and easier to distinguish from background stars. Now, a telescope isn't necessary for simply spotting Mercury, but if you want to see it as more than just a point of light, even a small telescope will reveal Mercury's phases, kind of like how the moon changes shape throughout its cycle. For photography enthusiasts, a camera with manual settings and a sturdy tripod becomes essential equipment, along with a telephoto lens to capture Mercury's tiny disk against the twilight sky. One piece of equipment that's absolutely crucial, regardless of your approach, is a reliable star chart or astronomy app on your smartphone. These help you know exactly where to look and confirm you're actually seeing Mercury rather than a bright star. And honestly, the most important equipment is actually your patience and persistence, because Mercury observation requires multiple attempts and perfect timing to master successfully. Duration of visibility. You get roughly 10 to 14 days of reasonable viewing opportunities centered around Mercury's maximum eastern separation, but here's the catch. Mercury isn't equally visible throughout this entire period. The peak visibility occurs on the exact day of maximum separation, when Mercury reaches its greatest angular distance from the sun and appears highest above the western horizon during evening twilight. On this optimal night, Mercury might remain visible for up to 90 minutes after sunset under perfect conditions, though typically, you'll have about 60 minutes of good viewing time before it sets below the horizon. As you move away from the peak date, Mercury's visibility window shrinks rapidly. Just 3 days before or after maximum separation, your viewing time might drop to only 30 to 45 minutes after sunset. The viewing window continues to compress as Mercury begins its orbital journey back toward the Sun, eventually becoming impossible to spot as it gets swallowed by solar glare. What makes this timeline tricky is that atmospheric conditions, your geographic location, and seasonal factors all influence how long Mercury remains visible each night. Northern observers during spring separations might enjoy slightly longer viewing windows, while observers at southern latitudes during winter separations face much shorter opportunities. The key insight is that Mercury's visibility follows a bell curve pattern. It gradually becomes easier to spot as maximum separation approaches, peaks for just a few days, then rapidly becomes more challenging until it disappears entirely. This compressed timeline means you can't procrastinate when Mercury becomes visible. Common viewing mistakes. You're probably sabotaging your own Mercury observations without even realizing it, and these mistakes cost countless stargazers their chance to spot this elusive planet. The biggest blunder is looking too early after sunset. Many people start scanning the sky immediately when the sun disappears, but Mercury won't be visible until at least 30 minutes later when twilight deepens enough to provide sufficient contrast. Another fatal error is searching too high in the sky. Mercury during eastern separation stays remarkably low, typically appearing no more than 8 to 21 degrees above the horizon, which is roughly the width of 2 fists held at arm's length. People also make the mistake of expecting Mercury to look like a bright, obvious planet when it actually appears as a modest, star-like point that's easily overlooked if you're not scanning systematically. Timing your observation session wrong kills more attempts than bad weather. Mercury's visibility window shrinks rapidly as you move away from the peak elongation date, yet many observers try weeks before or after maximum separation when Mercury has already become too faint or too close to the Sun. Geographic confusion ruins observations too. Northern Hemisphere observers often attempt to spot Mercury during autumn elongations when the ecliptic angle makes it nearly impossible, while the same elongation would be spectacular from the Southern Hemisphere. Don't confuse Mercury with bright stars or aircraft. Mercury appears steadier than twinkling stars and moves much slower than planes. Finally, the most expensive mistake is giving up after one failed attempt instead of trying multiple nights around the elongation peak. Photography tips. You can absolutely photograph Mercury during maximum eastern separation, but success depends on mastering timing, equipment setup, and post-processing techniques that most amateur photographers overlook completely. The golden rule for Mercury photography is shooting during the optimal twilight window. Start capturing images 30 to 45 minutes after sunset, when the sky has darkened enough to provide contrast, but Mercury hasn't set yet. Your camera setup becomes critical here. Mount your camera on a sturdy tripod with a ball head to eliminate vibrations, and use the longest focal length possible, ideally 200mm to 600mm or more, to make Mercury appear larger than a tiny dot. Manual camera settings work best. Shoot in RAW format, use a relatively small aperture like f8 for sharpness, keep ISO low at 100 to 200, and adjust shutter speed based on your light meter readings. The focusing technique separates successful shots from failures. Turn on live view, zoom in on Mercury digitally, and focus directly on the planet's edge until it appears tack sharp. Use manual white balance starting around 5500 Kelvin and adjust based on the color temperature you're seeing through your viewfinder. Take multiple bracketed exposures since Mercury's brightness can be tricky to nail perfectly on the first shot. Post-processing becomes essential because Mercury often appears too dim and small in the original images. Enhance visibility through careful brightness and contrast adjustments in software like Photoshop. The key insight most photographers miss is that Mercury photography requires patience and multiple attempts across several nights around maximum separation, since atmospheric conditions and timing must align perfectly for success. That's Mercury's maximum eastern separation decoded. You now know exactly when and how to spot the solar system's most elusive planet during its brief evening appearances. Mercury won't wait for you. These viewing windows happen only 3 times per year and last just days. If this cosmic knowledge sparked your curiosity about our incredible universe, smash that subscribe button and hit the bell icon so you never miss another Space Facts revelation. Drop a comment below and tell me, have you ever successfully spotted Mercury, or will this be your first attempt? Until next time, keep looking up and exploring the wonders above us.